Have you ever looked up at the night sky and wondered about its deepest, darkest secrets? What is the most extreme place in the entire universe? Many would say it is a black hole. Imagine a place in space where gravity has become so powerful, so overwhelmingly strong, that absolutely nothing can get away from its grasp once it gets too close. Not even the fastest thing we know of, a beam of light, can escape. This cosmic trap is what we call a black hole. It is less of a hole and more of an object, a massive amount of matter squeezed into an impossibly small space, creating a gravitational field of incredible intensity. To understand a black hole, you must first understand its most famous feature, the event horizon. Think of the event horizon as an invisible boundary, a perimeter drawn in the fabric of space itself. It is not a solid wall you could touch or a surface you could stand on. Instead, it is the ultimate point of no return. If you were in a spaceship and you drifted across this line, you would be caught forever. Where do these incredible cosmic monsters come from? They are not just born out of nowhere. The most common type of black hole, a stellar mass black hole, has a dramatic and violent origin story. It begins with the death of a truly enormous star, one much, much bigger than our own sun. Throughout its life, this giant star is in a constant battle with itself. The nuclear fusion happening in its core creates a massive outward push of energy and pressure. At the same time, the star's own immense gravity is trying to pull everything inward, crushing it all together. For millions of years, these two forces are in perfect balance. But all stars eventually run out of fuel. When a massive star burns through all the hydrogen, helium, and other elements in its core, the furnace at its center begins to shut down. The outward push from fusion weakens and then stops completely. Suddenly, there is nothing left to fight against the relentless, crushing force of gravity. In a fraction of a second, the star's core collapses under its own tremendous weight. The outer layers of the star are blown away in a spectacular explosion we call a supernova, one of the brightest events in the universe. While the outer layers are blasted into space, the core continues to collapse inward. If the original star was massive enough, not even the laws of physics that keep atoms from being crushed can stop the collapse. The material of the core is squeezed into a smaller and smaller and smaller volume. Let's talk more about this strange boundary, the event horizon. It's one of the most misunderstood concepts in all of science. It is not a physical surface, it's a location in space. If you were falling toward a black hole, you wouldn't feel a bump or hear a noise as you crossed it. There would be no signpost saying, "You are now entering the black hole." For you, the person falling in, the moment might pass without any immediate drama. You would simply sail across the invisible line, unaware that you had just passed the point from which no return is possible. The laws of physics as you experience them would not suddenly change at that exact moment. To help you picture this, let's use a simple analogy. Imagine you are in a canoe on a wide, calm river that flows toward a massive, inescapable waterfall. Far from the waterfall, the current is gentle. You can easily paddle against it or turn to the side and reach the shore. But as you get closer, the current gets stronger. There is a specific line in the water where the current becomes so fast that it is moving more quickly than you could ever possibly paddle. Once your canoe crosses that line, no amount of effort will save you. You are going over the waterfall. The event horizon is like that line in the river. Inside the event horizon, the nature of space and time itself is changed. So you've crossed the event horizon. What happens next? Your journey toward the center is not a gentle one. This is where we encounter a wonderfully descriptive, if terrifying, scientific term, spaghettification. It sounds a bit silly, like something from a cartoon, but it describes a very real and very powerful gravitational effect. The force of gravity you feel from an object depends on how close you are to it. The closer you are, the stronger the pull. A black hole's gravity is so extreme that this difference becomes noticeable over very short distances, even over the length of your own body. Imagine you are falling feet first toward the black hole. As you get closer, the gravitational pull on your feet will be much, much stronger than the gravitational pull on your head because your feet are closer to the singularity. This difference in gravitational force is called a tidal force. This tidal force would start to stretch your body. You would literally be pulled apart, elongated in the vertical direction. Your feet would be pulled away from your head, stretching you longer and longer, like a piece of spaghetti being pulled from both ends. That is how the process got its name. while you are being pulled longer, you are also being squeezed from the sides. Every part of your body is being pulled directly toward the single point of the singularity at the center. One of the strangest things about black holes has to do with time. According to Einstein's theories, gravity can bend not just space, but time as well. We call this effect gravitational time dilation. The stronger the gravity, the slower time passes. Near a black hole, where gravity is at its most extreme, this effect becomes truly bizarre. What you see happening to someone falling into a black hole depends entirely on your point of view. For the person falling in for a friend watching safely from a spaceship far away, the story unfolds in two completely different ways. Let's go back to your journey. For you, the person falling in, time feels perfectly normal. Your watch ticks along at 1 second per second. You cross the event horizon in a finite amount of time and continue your fall toward the center. From your perspective, your journey is a continuous and relatively quick one, although it ends with spaghettification. You would experience your own timeline just as you always have. But your friend watching you from the safety of deep space would see something completely different and utterly strange. They would never, ever see you cross the event horizon. As you fall closer to the event horizon, your friend would observe that your movements appear to be slowing down. Your clock would seem to be ticking slower and slower compared to their own. The light signals you send back, say from a flashing light on your suit, would become delayed and stretched out. The light waves themselves would be stretched by the intense gravity. If black holes are truly black and not even light can escape them, how can we possibly know they are out there? It's a great question. We can't see a black hole directly, but we can see its powerful influence on everything around it. One of the best ways to find a black hole is to watch the behavior of stars. Astronomers can observe a star orbiting something they cannot see. By tracking the star's path and its speed, they can calculate the mass of the invisible object it's circling. If the mass is huge, many times the mass of our sun, and crammed into a small space, a black hole is the only explanation. A perfect example is at the heart of our Milky Way galaxy. For decades, astronomers have tracked the orbits of a group of stars near the galactic center. These stars are whipping around an apparently empty point in space, some moving at millions of miles per hour. Their orbits show they are held by the gravity of a single, massive, invisible object. By measuring these orbits, scientists calculated that this object, named Sagittarius A star, has a mass of about 4 million suns. An object that massive and compact can only be a supermassive black hole. So, what is the final answer to our question? What happens if you fall into a black hole? The journey is one of cosmic extremes. From afar, you seem to freeze in time, fading away at the edge of forever. From your own perspective, you sail across the invisible event horizon into a region where space itself flows toward an inevitable end. You are stretched and squeezed by powerful tidal forces, torn apart, atom by atom. Spaghettification. Your matter continues its one-way trip to the central singularity, unimaginable density. Physics breakdown. But even this dramatic end is not the end of the story. Black holes force us to ask some of the deepest questions in science. What happens to the information that falls in? Do the unique details just vanish? Or is the information preserved on the event horizon, a cosmic hologram? These questions sit at the border between Einstein's gravity and quantum mechanics, and scientists are still working to find the answers. Black holes are more than cosmic vacuum cleaners. They are laboratories for exploring the limits of our knowledge.